Welcome to this next lecture on fundamentals of acoustics. We have so far seen sources and solutions of pressure field when sources are curved. When sources are curved, okay. Now I am going to discuss the physics of those solutions. Some point, okay. Now what I am going to do is, what if we have planar radiators, okay. Specifically, there is a problem called the piston or oscillating piston, in a baffle. Okay. So what do we mean by that? There is a disc. Piston is just a disc of, let us say, radius a, and it is placed in a rigid wall. Okay, so this is a rigid wall. Immovable, non-moving rigid wall. That is called a baffle. It's called a baffle. Okay. Now what does this disc do? The disc oscillates u0 e to the power j omega t. The disc oscillates back and forth with a certain velocity, a harmonic velocity, and so it radiates sound into this medium. Okay. So now the KH integral equation can be simplified if we have this planar geometry. We have this planar geometry, KH integral can be simplified. There are two terms in KH integral. If the geometry is planar, it can be made into one term. Okay. So that one term integral which results, okay, is called the Rayleigh integral. I think Rayleigh formulated it independently, and it can be derived from simplifications on the KH integral, and so it is called the Rayleigh integral. Okay. So we will first derive the Rayleigh integral, derivation of the Rayleigh integral. Okay. So now here is the scenario. I have initially an imaginary plane. I have an imaginary plane, okay, and there is a source, there is a plate of some area of some dimension, let us say, which is oscillating back and forth with some velocity, let us say u0 velocity v. Let us say z is in that direction, z is in that direction, positive, okay. Maybe x and y are here, x is like this, y is like this, z is up, okay. Now there is another plate right beneath this imaginary plane which has the velocity minus u0 ej omega t, okay, minus u0 e to the power j omega t, okay. So as this goes up, this goes down, and let me say that they are very close to the mean surface and this dimension is very small, okay. So I will close it, I will close the dimension, okay, so that I have now a box, okay, with very small negligible areas on the sides, and the top and bottom they move out of phase. The top moves up, the bottom moves down, okay. So now this is an enclosed surface, enclosed volume, okay, and we are interested in exterior sound. So how will the KH integral look like? Okay, let us say that I am interested in the pressure at some location x1, y1, z1. So the pressure at x1, y1, z1 looks like, let me write it simply, the top surface G del P dot n minus P del G dot n and ds of the upper surface plus integral the same thing G del P dot n minus P del G dot n ds lower surface, okay, and these are being ignored, those surfaces are very small, so they are being ignored, nothing much comes from there, okay. And the green function is of course G, the source points and the receiver points, okay. And if we convert all del dot n type gradients, del P dot n and del G dot n, we convert into z derivatives, okay. What do we get? We get P x1 y1 z1 is equal to integral. Now we are interested in exterior sound, so n points inward everywhere. So on the top surface it will point downward, in the bottom surface it will point upward, okay. So this del P del n is minus del P del z, so I get minus G del P del z. Similar reason plus P del G del z, okay, dsu. okay. And let us say we are at a distance, this top surface is at a distance a from the mean line, where z is 0, okay. So that is z equal to a, okay. So this top surface is at z equal to a. So the lower surface is equal at z equal to minus a, okay, and we will write that at z equal to a. Now on the lower side, del p del n and del p del z are in the same direction. So we get g del p del z minus p del g del z dsl z equal to minus a, okay. Now I'll need both of these, I suppose. So let me copy it, okay. Now g exact form in this Cartesian coordinate is pretty straightforward. The g has e to the power of minus j k square root of x minus x1 whole square plus y minus y1 whole square plus z minus z1 whole squared divided by 4 pi square root of x minus x1 whole squared plus y minus y1 whole squared plus z minus z1 whole squared. We will be looking at z derivatives all the way, okay. So I'll simplify this, the look of this thing. So I will write g as e to the power minus jk square root of, okay, c square plus z minus z1 whole squared by 4 pi square root of c squared plus z minus z1 whole squared. Okay. So now let us see, we need del g del z. So del g by del z, what is it equal to? Okay, add from this form. Okay, so the numerator, derivative of the numerator, okay, e to the power of minus j k square root of c square plus z minus z1 whole squared into derivative of the this exponent now, okay, which is d by dz of minus jk square root of c square plus z minus z1 whole squared. Of course the denominator 4 pi square root of c square plus z minus z1 whole squared, okay, that is the first term, minus e to the power of minus jk square root c square plus z minus z1 whole squared by 4 pi, okay, and the derivative of c square plus z minus z1 whole squared to the power minus half. Okay. Derivative of this into this minus derivative of this into this, that is all we are doing. Okay. So, what do we get now? We get e to the power of minus j k square root of c square plus z minus z1 whole squared. Now dz of that is jk is a constant, so minus jk is 1 by 2 square root of c square plus z minus z1 whole squared, and the derivative of z minus z1 whole squared with respect to z, which is 2z minus z1, okay, and divided by 4 pi square root of c square plus z minus z1 whole squared, okay, minus e to the power of minus j k square root c square plus z minus z1 whole squared by 4 pi, then derivative of something with a minus half is minus a half c square plus z minus z1 whole square to the power minus 3 by 2, okay, then d by dz of c square plus z minus z1 whole squared, okay. So that becomes, so let us do some simplifications. 2 goes away, so I have minus jk by 4 pi e to the power of minus jk, I will just put this here and here, then z minus z1 okay, so that becomes equal to doubling product, okay, then minus, so this entity is, what is this entity? This is square root of c square plus z minus z1 whole squared, minus again e to the power of minus jk, this entity, okay. Let me do minus 8 pi, okay, so this and this are taken care of. Then I have the entity to the power cube, okay, the square root to the power cube, and d dz of this is twice into z minus z1, okay. So that gives me a 4. So let us see what we can do now. I have minus jk by 4 pi let's hold on. So let me take this to 4 pi. So I have e to the power of minus jk square root c square plus z minus z1 whole square by 4 pi into z minus z1. This is common, this is common, this is common, this is common, this is common. Okay. Inside now I put minus jk by c square plus z minus z1 whole squared and a plus 1 over c square plus z minus z1 whole squared to the power 3 by 2. Okay. Okay. So now this is what del g del z. Okay. Now del g del z, del g by del z at z equal to a, okay, is e to the power of minus jk square root c square plus a minus z1 whole squared by 4 pi a minus z1 minus jk by c square plus a minus z1 whole squared plus 1 by c squared plus a minus z1 squared 3 by 2. Okay. Now let me take this to the next page. Okay. And then we have del g by del z at z equal to minus a, e to the power of minus jk square root c square plus a plus z1 whole squared by 4 pi minus a minus z1 minus jk by c square plus a plus z1 whole squared plus 1 by c squared minus a minus z1 whole squared, which is a plus z1 whole squared, a plus z1 whole squared to the power 3 by 2. Okay. So now we take on each of these limit a tends to 0. A tends to 0. Okay. What is the advantage, or what? Let's see. Let's do this first. Okay. So if we do that, if a goes to 0, then let me call it term 1. Let me call this term 2. Term 1 ends up looking like e to the power of minus jk square root c square plus z1 square by 4 pi minus z1 minus jk by c square plus z1 square plus 1 over c square plus z1 square to the power 3 by 2. Okay. Then if we take the second term, what do we get? We get z tending to 0 e to the power of minus jk square root of c square plus z1 square by 4 pi, okay, into minus z1 minus jk by c square plus z1 square plus 1 over c square plus z1 square to the power 3 by 2. Okay. So they are equal. So limit a tending to 0 del g by del z at z equal to a is equal to del g by del z at z equal to minus a. Okay. So what happens? What happens to the kh integral now? The kh integral now, so we have a situation of an imaginary plane. So let me explain what I am doing. We have an imaginary plane, and on that we have a source which is going up, the source which is going down. Okay. So that means this is equivalent to a situation where we have a source, okay, which is sitting on a hard wall. This is the physical picture. Okay. Why? If we have any oscillations, let us say this is small, okay, then we will have a situation of sound waves moving and getting reflected, okay, and they will appear to be coming from a source behind at a reflected point on the negative side. Similarly, if we have a ray that is going and it bounces with the Snell's law, we extend it back, okay, so then this ray will appear to be coming from somewhere behind. Okay. So that means what? If I make it an imaginary and put a source behind, if I make this surface imaginary and I put a source behind that is doing just the opposite of this, or if I put only one source and I put a rigid wall, they are physically equivalent. Okay. I suppose you see what we are doing over here. Okay. So now for this situation, mathematically I have found del G del Z at Z equal to A equal to del G del Z Z equal to minus A. So if we go back to the Kirchhoff-Helmholtz integral equation, and what is this? Because they are symmetric about this, if this generates positive pressure, this will also generate positive pressure. So pressures generated are same. Okay. So now if we go back and look at this term, del G del Z at Z equal to A is equal to del G del Z at Z equal to minus A. Okay. And in the physical situation both pressures are equal, but now they come with a negative of each other. The positive here, there is a negative here. Okay. So this P del G del Z term will cancel. Okay. So if I take this Rayleigh integral, copy this Rayleigh integral, let me copy this Rayleigh integral here. If I copy, then this term goes to 0. This term gets cancelled by this term over here. Okay. So what I am left with is just this here, integral minus G del P by del Z at Z equal to A ds upper plus integral G del P by del Z Z equal to minus A dsL lower. Okay. So now let me take this also to the next page. Let me take this to the next page. Okay. So now let us look at this. Del P by del Z from the Euler equation upper is equal to minus j omega rho V Z upper, and del P by del Z lower is equal to minus j omega rho V Z lower. Okay. But if we take V Z upper to be positive, it is the negative of V Z lower. Okay. Because the two planes are vibrating symmetrically with respect to this imaginary plane. It goes up, this goes down. Okay. And therefore what happens is that I have upper is integral minus G del P del Z minus j omega rho V Z upper plus integral G del P del Z lower, which is minus j omega rho V Z lower, which is minus V Z upper. and dsu and dsl, the area is actually same. Okay. So, if we now look at this, I have two negatives, I have two negatives. So, I get integral over the same area of the radiator twice g j omega rho, okay, v z upper ds. Okay. So, if I have a situation like this, okay, where I have a radiator close to an imaginary surface oscillating and another oscillating below the imaginary surface symmetrically, okay, then that is equivalent first of all to an infinite wall, rigid wall, on which there is a radiator sitting, single radiator sitting and oscillating. Okay. And if we have this situation, the solution for pressure is given by, okay, P now at a certain x1, y1, z1 is given by this integral over an area j omega rho, let us say Vz, e to the power of minus j k r by 4 pi r as the green function, and twice the green function into the surface area. Okay. So, the solution to pressure at a certain point x1, y1, z1 due to two sources placed symmetrically about an imaginary axis is the same as one of them sitting on a rigid wall. So, this solution is the same, physically it is the same, and this can be written as this, and this is twice the green function, twice the free space green function. So, we have found a new green function, we have a new green function. So, what has happened in the KH integral? Okay, we have found a new green function which is numerically equal to twice the free space green function, but its del g nu by del z on the surface is equal to 0. Okay. So, this works for planar problems. So, as a result, because this del g by del z is gone to 0, only one term survives in the KH integral. This term has gone to 0. So, this is a g nu, okay, g nu, because it goes to 0 on the surface, this term goes away and you are left with g del p del z, which gets doubled. So, now the Rayleigh integral, is this: pressure at a certain point R is given by the integral over an area of a radiator j omega rho, velocity in the z direction or normal direction, e to the power of minus j k r by 2 pi r into the area of the radiator. I will close the lecture here, we will continue in the next class. Thanks.